Hi, this is a video about ANCOVA. So just for context, this video is for a subject STA404, looking at the ANCOVA topic. However, anyone else looking at it, I'm interested in using how to use RCommander to do ANCOVA will benefit from it. So people watching this video, you probably are aware of two stats ideas previously. And it's ANOVA and regression. So both of them we've experienced as having a quantitative response variable, but the types of explanatory variables are a bit different. So for ANOVA, for example, we would have factors, so qualitative variables, and so you just got one of them, it's one-way ANOVA. If you start getting more of them, you can get two-way, etc. Then we'd say the simple linear regression. That's a simple one, is you've got one quantitative explanatory variable for it. And so for ANOVA, we seem to be comparing variances and working out which factors are significant or not. And then when we do have significant factors, using post hoc techniques to work out which different levels in particular are different. Where the regression, we tend to focus on equations. So what we're going to do today is to say that actually they're both really part of the same story. So and looking in particular at this idea of ANCOVA. So ANCOVA in particular is when you have a quantitative response, so same as the other two, and we have at least one factor, one qualitative explanatory variable, and a covariate, one quantitative explanatory variables, so have both together, and see the sorts of questions you want to look at. And the way we're going to do this is, in this video at least, I'm going to use RCommander to do as much of the legwork as possibly can to do all this sort of stuff. And what we're going to do is look at using linear models to do it all. So before I get into that, one of the things that's useful to think about is that even though we deal with factors, we would like to work out equations. So what we're exposing ourselves to here is, when we do ANCOVA, is we're trying to fit an equation or set of equations, depending on how you want to think about it, to our data. And so when we've got a covariate, a quantitative variable, okay, sort of makes sense. But when you're qualitative, how do you do that sort of stuff? And so one way of doing that is called indicator variables. Now, an RCommander would do it automatically on your behalf. You don't actually have to do anything, but it's worthwhile just taking a step back to explain a little bit the process. This is the indicator variables. And so this video, I'm just going to focus primarily on letting R do its work, but it is useful to understand some differences. So the study guide for STA404 goes in a bit more detail, which I won't talk about very much. But essentially, there's sort of two basic approaches for indicator variables. So in both cases, you pick some sort of reference group. So this is your reference level of a particular factor. R by default will just pick the first category, and if you go given anything else, it'd be the one earliest in alphabetical order. For the study guide approach, it uses the last category. So you pick a reference one. Then once you picked a reference one, there's sort of two standard ways of encoding it. The one the study guide uses is called effect coding, where each new indicator variable they make up would have an average of about 0. Whereas the one that R uses is an indicator, so it's just on or off. They look a bit different. The equations you get at first, the coefficients you get from both will look a bit different, intercepts, etc. But if you marry them all together, you get the same answers. So which one is better depends on what you're trying to do with it in the end. So for our purposes, using whatever RCommander spits out is fine, as long as we know how to read it afterwards, which I'll get to. For STA404 students, I encourage you to read through the study guide for a bit more information if you're interested in. But otherwise, we'll let R do its work. The other thing that's useful to consider is that all of these models assume that the random errors are normally distributed, which in practice doesn't always happen. And so when we are dealing with that, we can try to fix it up by transforming our data. And so the study guide goes a little bit more detail with that. So again, you can read it. So let's look at what ANCOVA is. So I said, I know ANOVA and a regression we can think of as a few different things, but ultimately at the heart of it is it's actually trying to fit an equation to the data. So ANOVA is you've got a quantitative response variable, and it'd be different depending upon which particular group it's in. And so often we think about it as getting different means for the groups. Regression is trying to fit an equation. So I got simple linear regression here. So it's fitting an equation to some data. Both cases have these random error terms at the end. So what ANCOVA is trying to do is fit an equation which has both the explanatory variable, both the factor and a quantitative variable. So it has them both together. So let's try to explain what this equation means. I'll do it algebraically on the screen, and then I will show you what it looks like visually as well. So this is an equation. So we're assuming we've got one explanatory variable. So the explanatory variable, I'll consider my example in a second, is we've got three different drugs we're trying to use. So there are three different groups. One covariate, so this would be, so our response variable is the post-response on some drug category. The covariate X here is what the level the response was beforehand, before giving the drug. And so what this equation means is, depending on which group, 1, 2, 3, it belongs to, we're fitting a different equation. So for example, level 1, so in this case, the drug with level drug A, then we're fitting an equation, just a normal straight line equation actually, to the data. So the intercept is the mu plus A1, and the slope is beta 1. And then level 2, we fit a different equation to it. So the intercept is mu plus A2, slope is beta 2. And the same thing for the third level. They all have error terms, which again we're assuming are all of these error terms put together are normally distributed. And so you're just trying to fit three different equations to it. And so this compact form we're writing at the top is trying to represent all that together. And so the fact that I write down alpha I is indicating that the intercepts for all the lines are different. And writing down beta I, little subscript I, indicates the slopes are all different. So, what we're going to do is we are going to use ANCOVA to fit these, collection of lines to some data. The questions we would normally ask with this is, well, okay, so we've got an equation. So what we are essentially assuming is that there is an interaction between which treatment it is, so the group, and the covariate. There's some sort of interaction going. That's why we're fitting different lines to them. Can we ask if there is an interaction or not? And so if there was no interaction, then the slope should be the same for all of the lines. So instead of writing beta I can just write in beta, indicating they're all the same. Or I might want to ask, well, is there a main effect for the treatments? So maybe there is no main effect, so I can get rid of it. So I can get rid of the alpha I. Or can I ask, maybe Y is not dependent upon X at all, and I can get rid of that variable? Or actually, does the fact which treatment it comes from not matter at all, and therefore I could just reduce it down to one straight line? And so what we tend to have is, we tend to have questions we would like to know. As you can see, questions in terms of understanding of a problem, and each of those corresponds to thinking of a different equation we can fit to the data. And so ultimately what ANCOVA is about is working on a bunch of models and comparing these models to answer the relevant questions we want to do. And usually our question is, okay, a whole bunch of ones, which equation is the best fitting one to the data? And once we have worked out which one is best fits, what is the equation? And therefore be able to use it. That's the idea. So let's look at what some of these equations look like in terms of pictures. So prepared something. So as I just clarify the example I was doing. So we want to test the effects of 3 different drugs, so A, D, F. And so there's the score given for the illness before the treatment was applied. That's called pre-numbers. And afterwards, I think post numbers. And so in a minute, I'm going to fit all these I'm going to fit all of these equations to it. So I just want to talk about what each of these equations might look like. So I've generated all these. You can see the code in my slides here. So the first one is the full ANCOVA model. So this is where I've got, so for simplicity, I've just dropped the mu term, so just basically set an intercept and slope, but it's the same as what I had in the other slide. The other slide's emphasising the effect nature. This is just emphasising the coefficient. We're just trying to work it out to it. So for the full ANCOVA, pretty much it's trying to say, I've got 3 different treatments, I'm going to fit 3 different straight lines. So this is an example. So 3 straight lines should fit to the data, just an example. And so in general, the 3 straight lines you're fitting could be nowhere different at all. It could be quite different, so nowhere similar to each other. Or it could be a bit similar, it could be anywhere between. And so the question often is, how similar are they? Is 3 distinct lines actually required or not? And so in terms of R, which is what we have to think about in a second, that particular model is thought of as being the Y variable is dependent upon the interaction of both variables together. So it's drug star pre corresponds to that. So it's I, full interaction between the 2 variables. The next one I want to consider is this model, and it's almost the same except that the slope is fixed. So this is the fixed slope case. So that would be, again, fitting 3 lines, but they're all the same slope. In terms of R, that's where you're just saying that the variable drug and pre both have an impact, but they don't interact with each other. So it doesn't depend upon which one's which, and therefore that's why the lines are parallel. So when you think of interaction plots you've done for, say, multi-way ANOVA in the past, again, for no interaction, expect parallel lines. Same idea cropping up here. So it's the no interaction term. Next model I've got here is different slopes for the same intercept, so all the same intercept. So this is in some way going, well, I'm assuming some interaction, but checking for no effects, for no main effects. And so again, I've put the axes on, so the grey lines are the axes, just so you can see what the intercept actually is, and see all of these have the same intercept of whatever is -3. This sort of model usually is harder to explain, and so I wouldn't really go for it, but it's fine. So in order to try to type this into R, there's a few different ways. You can see all the ones listed down the bottom here. So simply it's saying, I don't want to know what drug or pre is by itself. I just want to see just the interaction bit by themselves. So the drug column P is just the interaction part. You can think of it as being, I would like it to be based upon the pre part and drug P. So essentially what I'm dropping out from the interaction is I'm getting rid of just dropping drug by itself, hence fixing all the intercepts. That's what's the way of thinking about it. Or, as I've said, you can write it as the full interaction, but I don't want the drug part. So all of those are equivalent R code. The first one is actually what they would all simplify down to. If you do, if whatever you type in, the output can look a little different at first glance, but it's all equivalent. So the next sort of model is where I basically fix both the intercept and the slope together. If I just try drawing that, it's just 3 lines right on top of each other, right? And so in order to make it easy to draw, I've just made the bottom line slightly wider than the other ones on top, which looks like a very tightly wound rainbow perhaps from your screen. But that's what it's trying, and that's trying to say is that the factor, in this case, which particular treatment you use, doesn't actually make a difference. So certainly post depends upon pre, but there's no impact from which particular drug it is at all. And so that's just saying post depends upon pre only. That's our little model on the top bottom here. The other one is, what about if we just think there's nothing to do with the pre-variables, so only intercepts? And so that would look like this one here. And again, in R, post only depends upon just the categorical variable, pre has no impact. So they end up being horizontal lines. In this case, 3 different horizontal lines. And the last option is going, well, post depends upon nothing. So post depends upon, doesn't matter on what the pre-value is, doesn't matter what treatment is, so you're just getting 3 horizontal lines which are all the same. The way to write that down in R, it's a little different to what you expect. It might be is post is an intercept only. And to say intercept only, we just use one for intercept. So they're the theoretical sorts of things you might want to get, just to give a sense for what they all are. So let's go to R and just R Commander. So I've got R Commander. I've loaded my data. In this particular case, I've typed it in, generated it manually. And so I'll just pick drug comp from my data set, but you could indeed have it in a CSV file and load it in using the import data menu as well. Just to show what it looks like, I'm just going to highlight the name of the data set and press submit, just to show you what's there. So as expected, we've got our 3 main variables. What drug it is a factor, pre and post is our response variable. Just to show you, so although R will automatically give indicators, I've got some calculated here at the bottom as well on the side, but I won't use them for the moment. So just to give a sense for what an ANCOVA is actually going to do, let's just draw it. So we're going to go graph, we're going to draw a scatter plot. And so for the moment, so our X variable's pre, Y variable's post, so that's just going to show you the data by itself, but we want to see what the different treatments are. So if we do plot by groups and pick the drug, and I'll just go okay for the moment. So what this plot's doing is it's just showing, it's just showing is the data, right? So it shows you the drug A's or the blue circles, for example. And then what I could do, again, first from that graphing menu, so back to the scatter plot, I can go to options and I can say, give me a least squares line. And what it does, because I've put the grouping variable, it puts 3 different lines down. So essentially, finding those 3 lines, that's what ANCOVA does. It's actually just finding those 3 lines for us. So what we can do elsewhere with it is going, now we've got our 3 lines. Are those lines the same? Are they different? So for example, is there an interaction? Is there evidence to suggest that actually they really are parallel? Or is there enough evidence to suggest they are different? So that's the sort of questions we've got. There's a bit of variability, right? So you can see some of the vertical spread here is quite substantial about some of these lines. So there's quite a bit of variability. So we should do some hypothesis tests for that. So in order to actually be able to do some, the hypothesis test to compare things, we will need to get them all in. So I'm going to do it really quickly. So I go to stats, fit models, and it's a linear model. And then post, I'm going to post is my response variable, and I want to do my first one. So the first one I'm going to pick as the most complicated model and then simplify down from that one. And so the most complicated model is I've got drug and I want it to be the full interaction with pre. So that there, as I've just typed it in, as I said before, that's the full ANCOVA model. So I'm doing both a factor and a covariate put together, and I want to have full interaction. That's the full covariate model. So because I want to type lots of these in quickly, I'm just going to hit apply for the moment. So what it does is it does the model for me, does some things in the background, which I'll show in a second, and then pops the window back up. So it's given me a new model name. This time around, I want to give the simpler one. So the simpler one was the plus case. So this is basically parallel lines. Hit apply. Model 3 is I just want all the intercepts to be the same. In that case, I'm using colon, so I only want to see just the interaction between them. And hit apply. 4 was I just want one straight line, so I don't really care about drug at all. Just remind myself that's right. Yep. So 4, hit apply. 5 was I just want a drug only. So you probably can't see what I'm doing, but if you just double click on one of these names, it just pops it in there for you. You can also type it in just as easily. Hit apply, and the last model was that post depends on nothing, so I just have an intercept only, so type in 1. Now I've done them all, I press OK. So you can see what it's done at the top, just the code it's putting in, is it's generated each of the different models. So that line there, for example, generates that first model for me. And then it gives me a summary, so it just gives me the output. So just so we can see, I was going to highlight that one so I can put it on the bottom. So it adds it, and essentially it's treating it like regression. So therefore it's working out what the intercept is, that's the intercept there, and a whole bunch of different coefficients. And we'll have to use these later if we think this is the right model to use. It does tell you significance of individual coefficients if you care, but what's perhaps more useful is being able to compare as a group. And so the way to do that really is having some sort of ANOVA tables is really helpful. So a few different ways of doing it. So whenever you've got a model, it's good to get some more information. So I've got lots. So if you click the models menu, we've generated lots. So let's go back to linear model 1, make sure we're the right model. And the models menu does lots of things. So as you might remember from previous, if you go down to graphs, basic diagnostic plots, you can use that to check for the assumptions. So if the assumptions are okay for the most complicated one, it's going to be okay for everything else too. I won't do that right now. But if you go down to hypothesis test, that's the thing I want to focus on. If you do a ANOVA table, for example, just hit OK, this will give you, summarize all of those different things as one ANOVA table. So what the great thing is here is you've got a whole bunch of interaction terms. They've got 2 different rows for interaction, 2 different rows for drug, etc. And so the ANOVA table just collapses them all down, which is really useful. And so when we got this table, even though pre is a covariate, so it's not a factor, we can read this table off just like you've done for 2A ANOVA. And so what you'd normally look for in a table like this, if it was just 2A ANOVA, would be look at the interaction term. That's the thing you look for first. And so since the interaction there is much bigger than 5%, we would reject the corresponding null hypothesis and say there's no significant difference with the interaction, i.e. we could get rid of it. So we might as well. So therefore, that suggests that there's not a sufficient evidence to suggest the lines are not parallel. Let's put it that way. So although this table is really helpful, maybe what we should have been doing is not focusing on the line being parallel, but maybe the intercept being the same. Instead of being the line or the slopes the same, maybe the intercept being the same. So you might want to compare different models. So the other thing you can do with it, so although these ANOVA tables is useful to read off some numbers, what we often want to do is we want to compare different models. So 2 different things you can do. One is option one is, so first scenario is when the two models are nested. I.e., a nested model is you can get from one to the other by just fixing some of the numbers. So making some of the coefficients 0 or making some of the coefficients equal to each other. So the no interaction term is just pretty much making all the slopes the same. Like that's a nested model. So to compare those, we go to models, hypothesis tests, compare two models, and you pick the one. So model 1 is the full one. Model 2 was my equal slope scenario. And what it's doing, it does what's called a partial F test. And so if I did the ANCOVA table for the linear model 2, it's taking some differences between both degrees of freedom and the residual sum of the squares and doing a partial F test. So this is the partial F test for it. So partial F test is a way of comparing two models. So if you notice, that p-value is the same one we worked out before from the ANCOVA table, because the only difference between these models is an interaction term or not. So again, by comparing these two models allows us to see it does do, is there an interaction? Or putting it another way, are the slopes different or parallel? And so what I would do from this is to go, well, by looking at this, I would suggest that that model 1 and 2 are not significantly different to each other, so you might as well pick the simpler one. Which model is simpler? Well, the one with the lower degrees of freedom. And so model 2 is lower degrees of freedom, so less things you're trying to fit to the data. So that would be the better model to pick. Can I do better? So I'll come back to the second scenario in a second. But so what we could do is we could compare all the different tests. We just keep going down the line. So here's some code I prepared earlier to do it all in one quick go for me. Let's see if it works. So here's the output from the end. So what I've got the ARCO to do is comparing different models. So so this top row is the one I've just looked at. So I want to compare models 1 and 2. So I did the partial F test for it, and this is the p-value it gives me. And as I said, the purpose for comparing those two is just to say, are the lines parallel or not? And because they're not significantly different, there's no evidence to suggest they're not parallel. You can I've listed all the other different nested models we can consider. So 1 and 3, for example. So 1 is the full model, 3 is the equal intercepts. So essentially, are the intercepts equal? By looking at those, well, actually, there's no significant difference. So again, model 2 and 1, no difference. 1 and 3 are no difference either. And so I might as well pick, so either of them is better than the original one. Is one way of putting it. But you can answer the question is, well, which one's better? But you can keep going down, right? So if you can compare model 2 and 4, no difference. So therefore, then once you get down, 4 is the simpler one. Then you can compare 4 and 6 and go, well, that p-value is pretty small, right? That's much less than 5%. So therefore, model 4, which is essentially saying one straight line, that's better than having no lines at all. So that's trying to say that pre does have an effect. Definitely pre's got an effect. That seems to be the best one. If you trace the other one down, the 3 model, so comparing 3 and 4, so you can compare lots of them. So I won't talk all of them. But essentially, what that does suggest to me suggests that model 4 appears to be the best one. So if you go 1 to 3, they're the same. 3 to 4, no significant difference. So therefore, model 4 seems to be the best option from all this. So what I've done is done partial F test. So really, it's the same as just doing that hypothesis test, compare two models multiple times. That's all I'm really doing. I've just got the computer to dump them all for me quickly. That is useful to compare models which are nested. Not everything's nested though. So for example, in this case, well, it's pretty I could work out that model 4 is the best by just going through the nests. But maybe that doesn't always work. So, for example, maybe models, 2 and 3 end up being the same. So 2 is fixed slopes, model 3 is fixed intercepts. How do you tell them apart? They're not nested, like they don't exactly match each other. So the way to do that is to use a different measure. So using some information criteria. So there's 2 listed here. So I'll pick the first one, AIC. And so I just type in AIC and it just gives me the AIC for that model. And I could do it for lots of them, right? So so you can do it from individually, or you can type a few in one go. So if we just go down there, so you type a few in a row, highlight it, and press submit, and it gives you all the different AICs, as well as degrees of freedom. So just again, here's some code I prepared earlier to get lots of these things together. So what I've done here is a generated table, got all the models, worked out both AIC, which is one information criteria, BIC, Bayesian information criteria, and then a measure of fit. So MSE is the mean squared error. So that's a way of working how good the fit is. So MSE, the smaller the better, usually what we think about it. And N parameters is the number of coefficients we're using in the model. So essentially, let's ignore information criteria for the moment. The smaller the MSE is, the smaller the standard deviation of the random errors are. That's what it's really trying to estimate. And so the smaller numbers there are better. For the number of parameters, keep it simple, stupid, is the moral of the story, really, right? And so for keeping it simple, stupid, we really do want to have the smaller number of parameters. So again, a smaller number is better. And you can see that they sort of go in opposite directions. As you're going down, the models go from complicated to simple. The MSE tends to blow out a bit, which tends to happen, right? So the more complicated the model, the better chance of reducing error. But as it gets simpler, that's better. And so it normally is some sort of compromise you want to try to pick. So these information criteria are trying to compromise those two different ways. Trying to compromise the actual fit of the model versus the complexity. It's trying to put both together in some sensible way. So slightly different ways of judging it. So essentially with these information criteria, lower numbers are better. So smaller numbers are better. If they're within plus or minus 2, then we'll call they're about the same in all intents and purposes. And therefore, if 2 things are about the same, you might as well pick the one with the lowest number of parameters. So if you look at the AIC, that's what I've got. The smallest number here is model 3. So that would suggest that model 3 actually might be the best. But then you're going, well, but within that, as a matter of fact, model 2 and model 4, although they're not quite as small, they're all really in the same ballpark. So essentially from AIC, what I would actually conclude is that models 2, 3, and 4 are all about the same in terms of the amount of information they give you. And therefore, since they're all about the same amount of information they give you, we might as well pick the one which is the simplest. And therefore, hence we pick model 4, because it's got the least number of parameters. So you get the same conclusion. BIC is clearer, right? So that really is the smallest one. And so taking a step back, ANCOVA basically is a way of generating, fitting a bunch of equations to our data when you've got mixed explanatory variables. What we tend to do with this stuff is we want to compare a whole bunch of models to work out which particular coefficients we should be using or not. And so you end up getting a bunch of models. With the models, we have 2 ways of comparing them. So way 1 is using a partial F test. And the way to do that is to use the hypothesis tests compared to models feature. The other way is to use information criteria, which can be used to compare any models at all, but in particular, you definitely need to use them when comparing non-nested models. And so there's two different information criteria functions available here. They should normally give you the same result. They're slightly different. So that's our different ways of comparing it. So from all that, you can go through them. I've skipped some steps clearly, but in either case, we can go, well, model 4 is the best. So that's one that fits the data the best. So the question is, how do we work out what that line actually is? And so to do that, we need to find, so click model 4, that's the one we want, right? And if you go models, so let's summarize the model and hit OK. This gives you the coefficients that we would get. So it would be the summary. It's probably well and truly up on my feed here, but it would have calculated earlier. But these are different coefficients. So what you can see here is actually model 4 is actually simple linear regression. So you might be able to read it off. And so you can see that the equation is, I'll just type it in, post is equal to the intercept plus the slope times by pre. So that's the equation that we get here, and I can just read it off. So that's fairly straightforward in this case because it's simple linear regression. I could draw it. So again, if I go to my scatter plot, let me just turn the line off. So that's the data without the line added onto it. And then what I'm going to do is I'm going to basically want to put a line. So AB line is a way of putting a coefficient, so intercept slope line, that's what the AB stands for, line onto the graph. And I would like to just use the line coming from a regression, and the regression model is linear, a model 4. So highlight that, press submit. And what it does is it just drops the line on for me. So it just draws it. So essentially, what our best model is, and that particular straight line. So that straight line best fits the data. So it's trying, and in terms of words, the post values fully depend upon the pre-value. So, and that line explains the relationship between the two, or the average relationship at least. Whereas what particular drug you had didn't have any impact. That's why all the lines are the same. So that's how you can sort of draw it. Okay, that was fine in this case. What happens if you had a different one? So let's go to model 1. See if we can try to make sense of it. So again, let me summarize it. So we've actually seen this output before. I showed this. This is the one I showed you at the very beginning. So it's got a whole bunch of numbers here. How do I use these to work out what the actual equation is? And as I said, this is in terms of drawing, it's easy to draw all of them, right? So that's the drawing all of them. That's the graph I showed earlier. So that's the 3 different lines that's fit. How to work out what the equation is? So obviously the computer's done it magically for us, but how do I write them down? How do I work them out? So let's do A. So as I said, R by default chooses the first category, so drug A in this case, as our reference category. So let's work at what this blue line is for the moment. So when we look at the intercept and the pre, that gives you the answer for the reference category. So if I just do drug A, so I can read this off, right? So drug A would be the post variable is equal to the overall intercept plus the overall slope times by pre. So that's what the equation is for the simple one. Okay, that's fine. The other one's slightly more complicated. So let's do drug. F. Yeah, sorry. Drug F, so the third one, that's what I'm looking for. So the letters are not in order. Throws me off. So so drug F, we'll do the third one. So to do drug F, then this is where it gets complicated. This is where we have to think about it. So essentially we have our reference scenario, right? So the intercept and pre are still the reference values. So I'll copy that down. But the other, anything to do with F, so the two different labels with F, so this one's the first one that's got F with it, is what we add on in addition to the reference phase. So this number here is what we're going to add on to for drug F in addition to what we have as a baseline. So I just copy that and I have to paste that in. So that's what, so our intercept is changed by minus 1.47. So this is not telling us the intercept for drug F, it's telling us the difference between drug F and drug A for the intercept. That's what it's trying to tell us. That's where you have to think a bit more about it. Similarly for the slope, this one tells you how the slope is changing. So I just got to copy this value down. So that's telling us how the slope is changing between them. So let me just draw that. So again, I'm going to go back to my scatter plot and get rid of my line. Just before you can just see the line's supposed to be up here somewhere. So you could just visualize it just to see how well it's going to go. You can see I've removed it. So this time I want to use this AB line function to be able to draw it again. And so quite I prepared earlier. So A, so the intercept is going to be the first number plus the second one. So you can see I've just pulled it. So I've used the code to actually get what exactly for me. And the slope is the sum of those two numbers. So again, I've just put them in here using full code. If I highlight that, press submit, it didn't work. I didn't know it. I can't see. No. I cannot see what I did wrong at first glance. Oh well. Instead of you trying to work out, wait, me working what I did wrong. This is what it should be. There it is. So we can see here, this is the plot it should generate. So it should be just that top line. It should be appearing. And so what we are, so back to the point of it all is that even though we've got this model, we try to know what the equations are its fit. By using the right fields carefully, we can deconstruct it. And what we have to do is for each of the different levels of the factor, A, D, and F in my case, I have to reconstruct the three different lines by comparing values. Always use the basic one. The intercept and the slope tell you what the reference category is, so A in this case, and then I have to add on the other core values to work out what the relative ones are. So D would be, the sum of the first two numbers would be the intercept for D, for example. So I hope that helps you a bit with ANCOVA. So basically what we covered is how to generate an ANCOVA model using our commander from the Fit Models menu, how to use the Models menu to do some hypothesis testing. So looking both generating an ANCOVA table, using a partial F test to compare different models, and using information criteria to compare them, and using the summary of the model to actually work out the coefficients and work out what the actual data is. And on the side, I also looked at how to use graphs to display some of this stuff. Hope that was helpful. Thanks very much for listening.